All right, so what I'm going to do next is we're going to go ahead and calculate pH for strong acids and bases, and we'll also do pOH just for fun as well. But having said that, here's the thing that's important to remember. We assume that strong means completely ionizes. Okay, that means 100%. So you have HCl in water, right? And when it reacts with water, you're going to get hydronium and the conjugate base chloride, right? But because it completely ionizes, the concentration of hydronium is equal to the concentration of the acid. So if you want to calculate the pH, it's just a negative log of, sorry, 1.34 times 10 to the minus 2. That comes out to be 1.87289, right? It goes on and on and on. But there's three significant figures, so I'd be rounding it to that point. And so the pH is 1.873. Now, if you want the pOH of that solution, it's easy to get from here because the pOH is just going to be 14 minus the pH. And so that value ends up being 13.1271. So we'll just write it as 13.127. Again, 3 sig figs. For the sodium hydroxide now, sodium hydroxide is a strong base, and so it completely dissociates to form sodium ions and hydroxide ions. So that means the molarity of hydroxide in sodium hydroxide, because it's a strong base, is actually 1.64 times 10 to the minus third. Now, that being said, if you want to calculate the pOH for that solution, again, it's negative log of 1.64 times 10 to the minus third. And that's going to be equal to 2.785. And then to get the pH, all I have to do is 14 minus pOH. And that ends up being 11.215, like that. Now, the next one is related to oxide. And what happens when oxide is put in water, right? And again, if it's only got the one proton associated with it or the one negative charge associated with it, it's pretty simple to sort of assume that you get like a one-to-one stoichiometry. But oxide's different. If you take oxide and you combine it with water, we already saw that it made OH minus plus OH minus when combined with water. So what does that mean, right? That means for every mole of oxide, I get 2 moles of hydroxide. So to calculate the pOH in this case is a little trickier. So I have 0.10 mole of oxide, and then it's 2 moles of hydroxide for every 1 mole of O2. And so from that, even though this looked like a super simple problem at first, we end up with 0.20 molar OH minus. And so when we calculate the pOH, we have to take into account the stoichiometry of the reaction. Again, we saw that reaction when we wrote it here. This is the Bronsted-Lowry reaction 4, and then oxide was one of those, okay? So we'll get back to here and we'll calculate what the pOH is of that solution, and then we'll calculate the pH as well. So I'm going to take the negative log, pOH, right, is equal to the negative log of the hydroxide ion concentration. So that's going to be negative log of 0.20. And that comes out to be 0.69897. Two significant figures here, and so that becomes 0.70 for the pOH. Now, the pH is equal to 14 minus the pOH, and that'll be 13.30, doing that subtraction, right? Because it has to add to 14. So let's say now we're going to take a strong acid and a strong base, and we're going to mix them together, and we want to calculate the solution pH. I want to sort of walk you through that process. It's very similar to the ice table that we did, but we're going to use a limiting reactant assumption when we do the ice table. Okay, so we're not actually doing equilibrium, we're just going to do limiting reactant. So first of all, you have to write the reaction. And remember what I talked about earlier when we were looking at these acid-base reactions, that when you have two OH minuses here, it's going to take two HCl. So I know the stoichiometry of this reaction already. The product is going to be the salt of calcium and chloride, which is calcium chloride, and produce water as well. So let's write the reaction. We'll write CaOH2 plus 2HCl. And I knew that already because of what we talked about before. Oh, it's not an equilibrium because it's strong acid, strong base reaction. It basically just goes to completion like this. And then I'm going to have CaCl2 plus 2 H2Os. Okay. Now, I'm starting off with 0.020 moles of calcium hydroxide. And my HCl, I'm starting with 0.019 moles of HCl. So I know this reaction is going to the right because I didn't list any products. And what I'll end, this is my initial, this will be my change, right? I'm going to go down by X here, and I'll go down by 2x here, and I'm really only interested in the reactants because I'm wanting the pH. I just need to know how much hydroxide and how much hydronium is left in the solution. The products don't really interest me in this calculation, but if you were to fill this out, you would be going 0, 0, x, and x. Okay. Now we have to do a limiting reactant, and the limiting reactant is when one of the reactants runs out or goes to zero, right? So what you can do is just say, what if this is final, right? Not equilibrium. If this goes to zero, then x is equal to 0.020. But if this one goes to zero, then 0.019, right? Minus 2x is equal to 0. So x is equal to 0.019 divided by 2. So what that actually gives you is 0.0095. Like that. Okay, now you notice that this value for x is smaller than this value, so this is the limiting reactant. When x equals this value, then the HCl concentration will have dropped to 0, can't go any further, and then you'll have an excess of calcium hydroxide. So now what I do is I go back to my equation. And my equation is this, and this, I hope this doesn't confuse you. I'm going to erase this. Oops. I'm going to erase this. But again, I needed to do that to check it. And I'm going to say 0.020 minus, and my x value is actually 0.0095. 0.0095, like that. Okay? So that means the concentration of calcium, or the moles of calcium hydroxide, is equal to 0.0115 moles. Now, in order to calculate the pOH from this, right? Put a little thing here. What I need to do is convert that into hydroxide. Now, based on what we've talked about, you'll notice that there's two OHs in here. So what you need to do is to take this number and basically double it to get the number of hydroxides that are coming out of it. So the concentration of hydroxide is going to be equal to 0.0115 moles times 2, and then it's in 2 liters. And that gives you your molarity. So the top calculation represents my moles, and the bottom is just to convert it over to molarity. And that comes out to be, yeah, I just saw a mistake in here. This is actually, sorry, go back up for a second. This is 105. And so this is 105 up here. Oops. Ooh, it's weird. It's not zoomed, and it is 105. There we go. So times 2 and then divided by 2. So my molarity ends up being 0.0. Oof. 0.0105, like that. So the pH, or the pOH for this solution, because I have the hydronium, is just negative log of this value here. And that comes out to be 1.979. So that means my pH, I should have made a bigger slide, huh, is equal to 14 minus this value, 1.979. And that's 12.02. Which makes sense. It's a basic solution, so the pH should be high.